So consider two rectangular prisms. One has a height of 2, it has a length of 4, and it's going to have a width of 3. The other prism has a height of 4, a length of 8, and a width of 6. We say that these two prisms are similar, meaning they are the same basic shape, but they have different sizes. And in particular, we say that these two shapes have a scale factor of 2. Now our question is, what does it mean to say that these two similar prisms have a scale factor of 2? Well, that means that any length that we measure on the smaller prism, when multiplied by 2, gives the corresponding length on the larger prism. So you look at the heights, 2 times the scale factor of 2 yields the larger prism's height of 4. If we look at the lengths, 4 times the scale factor of 2 gives the length of 8. And if we look at the widths, 3 from the smaller times the scale factor of 2 gives us the width of the larger one, of 6. In each case, the small measurement times the scale factor got us the large measurement. And this process works for any linear measurement we would take on this shape. The perimeter of the face that faces us is 1/2 of the perimeter of the face that faces us on the larger one, for instance. But something weird happens with volumes. The volume of the small prism is length times width times height. So it's going to be 4 times 3 times 2, which is 24, whatever these units are cubed. The volume of the big shape is also going to be length times width times height, the formula for finding the volume of any rectangular prism, which means the volume of the big shape is 8 times 6 times 4. The volume of the big shape is 192 when you do that multiplication. But we've run into an issue here. Our scale factor is 2. Any measurement I take on the small shape when multiplied by 2 should get me the volume of the big shape. But the volume of the small shape times 2 would be 48, not 192. So that means that volumes have a different scale factor. Now, in facing a question like this, mathematicians try to find underlying relationships. They want to see that does what they're looking for have anything to do with what they previously know. And so let's take a look first at what is the scale factor between these two volumes. 192 divided by 24 equals 8. The scale factor for volumes is 8 when the scale factor for lengths is 2. So now we ask ourselves, does 8 have any relationships with 2? Our goal is to see, is something going on with this 2 that turns it into an 8 that we can then generalize to other cases. Otherwise, we'd have to find the volume for similar figures every single time if we ever want to figure out what their scale factors are. So I think about, what are 8's relationships with 2? Well, I know that 8 divided by 2 is 4. I know that 2 plus 6 equals 8. But these things all seem kind of arbitrary. I'm not seeing any clear relationships that really jump out at me that have something to do with volume. But then I ask myself, well, what do I know about volume? Well, volume is measured in cubed units. It has to do with finding how many cubes of a certain dimension could I fit inside an object. And I notice this relationship. 2 cubed is 8. We cube our units to get a volume. Does it make sense to say that we cube our scale factor to get a scale factor for volume? Intuitively, it makes sense. But we need to have something stronger than that. We need to have a proof. Some concrete reason to say this relationship has to be true no matter what shape we are dealing with. When we try to make proofs, one good way to approach it is to start by thinking about this specific situation and seeing if there are any patterns that emerge that we can then apply to a more generic case. In this case, our small volume is 2 times 3 times 4. Our scale factor, which I'm going to abbreviate with the letter C for constant, is 2. Scale factor is a constant, meaning it's a number. When I found my large volume, that was the same as finding 2 times 2 times 2 times 3 times 2 times 4. When I found this volume, it was 4 times 8 times 6, or 4 times 6 times 8 rather. But I could also express that in terms of the original box. I took this dimension, multiplied it by 2 to get this one. This times 2 gets this. 3 times 2 gets me 6. So I could think of the volume of the large box as take the height, take the width, take the length of the small box, multiply them by 2, and then multiply them all together. Now, multiplication is commutative. When everything is at the same level of the order of operations, these parentheses don't really matter anymore. I can regroup these numbers however I like. I can do whatever order of math I want when it comes to just doing multiplication straight across. I can associate these numbers in a different order as a result as well. So instead of doing 2 times 2 times 2 times 3 times 2 times 4, I can think of this as 2 times 2 times 2 times 2 times 3 times 4. I've taken all of these 2's, and I'm going to multiply all of them first out front. And then I took all of the actual dimensions and I multiplied them over here. This lets me say that the volume of the large box equals 2 cubed times 2 times 3 times 4, which is the volume of my small box. Huh. I have a reason to now write that the volume of the large equals my scale factor cubed times the volume of the small. Let's see if that works if we keep things generic. What if instead of a specific box, I have a generic box? Has a length of L, has a width of W, has a height of H. And my scale factor is going to be C. My larger box that got scaled up with a scale factor of C should have a volume of C times L times C times W times C times H. I scale up each of the dimensions for the smaller box to get the dimensions of the larger box. I multiply those 3 dimensions together to get the volume of the larger box. Because multiplication is commutative and associative, I can rearrange the order and choose to do certain parts first if it makes life easier for me. So I can rewrite this as C times C times C times L times W times H. All I've done is change up the order of the multiplication here, which means I can write V large as C cubed times L times W times H, which means my large box, no matter what its numbers were that got plugged in there, is my scale factor cubed times the volume of my small box. So our big takeaway, if we are scaling up similarly sized or similar objects will have a scale factor that relates their linear dimensions to each other, anything you can measure with a ruler. But their volume is going to have a scale factor that is the cube of that linear scale factor. So the scale factor for volumes is the cube of the scale factor for lengths.